My name is Jiaqi, a PhD candidate in the University of Maryland, and today I'm excited to present my work, the HEC, the equivalence verification checking for the code verification via the equality saturation. This is a joint work between the University of Maryland and the Pacific Northwest National Lab. Today's compiler performs the source-to-source code transformation, and it's common in the today's compiler. And however, the equivalence checking for the code transformation is critical, but sometimes it's overlooked. Consider we have optimization chain, and from the source code to destination code, and we have some of the compiler optimization technique, including the loop unrolling, loop tiling, loop hoisting, and along the optimization chain, if some of the bug may be generated without formally verified of this compiler optimization, we may even notice of this generated bug. So how can we verify this compiler performs correct compiler optimization? So the compiler optimization includes the datapath and the control flow transformation. And the datapath transformation includes the arithmetic and the Boolean rewrite. The arithmetic rewrite it includes it performs the arithmetic and the Boolean level of the rewrite, including the arithmetic law and the De Morgan's law. For the control flow transformation, it directly modifies the code structure. The common control flow transformation, including the loop unrolling, loop tiling, loop hoisting, and etc. So our problem is, how can we provide a unified verification manner for both of the data paths and the control flow transformation? Here we provide 4 of the code snippet for the baseline code, and we perform 3 different code optimization, including the loop hoisting, loop tiling, and De Morgan's law. It represents the difference of the data path and the control flow transformation. The De Morgan's law is the data path transformation. It converts the A and B into not A or not B. And the loop hoisting and the loop tiling is the control flow transformation. For the loop hoisting, it moves the constant truth into the loop body. For the loop tiling, it turning a flat loop into a nested one. So how can we verify this 4 different compiler optimization in a unified manner? And we will use this 4 code snippet as a motivation example to illustrate how they are included in our framework. The existing tools are limited to the specific transformation domain. For example, the polycheck is focused on the control flow transformation for the affine program. And there is also some other SMT-based data path transformation tool. And they are focused on the data path transformation, and they can handle the control flow transformation. So none of them can provide a unified manner. And this is the problem we are trying to address in this framework. The code equivalence checking reminded me of the eGraph data structure. It is the data structure to provide a compact representation of the equivalent terms. It allows us to explore all of the possible rewrite of the input program and capture the semantic equivalence by merging all of the equivalent forms into a single E-class. Here we provide an example of the eGraph. We provide the eGraph input, the eGraph output, and we label the E-classes and the E-nodes. So it's more example of the eGraph from the left to right with the different writing rules. eGraph rewriting and the equivalence checking both seek a sequence of the valid paths that maps one program into another. So for our problem, the code equivalence checking, the problem can be turning into can we show the original and the transformed version of the program can be collapsed into the same equivalence class? We proposed the hack. It's a hybrid equivalence checking. It is based on the e-graphs, and we targeting in the MLIR code. We aim to provide a unified manner for both of the control flow and the data path transformation. It takes both of the static and the dynamic writing rules. The static rules for the data path transformation and the dynamic rules for the control flow transformation. We will talk about the writing engine and our inner graph representation and the eGraph runner. We create a custom ASD-inspired graph representation. In our representation, each of the graph nodes will be translated into the represent the MLIR operation, and each of the graph edges represent the data dependence and the variable paddings. We provide the graph representation for our baseline code. Here we will extract the technical parameters like the loop boundary, loop steps, and the variable padding for the loops. And we will isolate the loop bodies for preserve the data dependence and the evaluation order. Now let's give a quick recap of our motivating example, the loop hoisting. It moves the constant truth into the loop body. We can see both of these two code snippets can be represented with the identical graph representation because they have the same data dependence. So both of them can be unified into the same graph representation. It allows us to automatically verify these transformations like the loop hoisting before we perform the eGraph rewriting. This is the static writing rules. We have incorporated over 60 static writing rules ranging from the arithmetic to the arithmetic log to the Boolean identity. All of the static writing rules perform the data path and the arithmetic level writing. Based on this static writing rules, we can collapse this program into the E-classes even before we perform the eGraph rewriting. Here is another motivating example of the De Morgan's law. The two of the code snippet for the baseline and the De Morgan's law, they can can share the same E-classes and merge into the same E-class to prove the semantic equivalence. This is the hybrid eGraph writing rules. So why we need the hybrid writing rules? We know that when we perform the control flow transformation, it will generate some of the runtime dependence parameter like the tiling factors, unrolling factors, and some other variables that is only generated information. So the static writing rules cannot handle such key information. So we propose the dynamic writing rules. For each of the control flow transformation, we will create a rewriting pattern and create a corresponding writing rules. And we use these three SMT solver to verify the transformation conditions. This is our final motivating example for the loop tiling. It turns a flat loop into a nested one. In this figure, we have shown the corresponding dynamic rewriting rules. Now let's talk about the heart of the eGraph runner. The heart of the hack, it is the eGraph runner. The input is the graph representation of the MLIR code, and it takes the static writing rules for the data path transformation and the dynamic rules that is generated in the runtime. It takes the static rules. Here is the process. We will apply the static rules and attempt one round of the equivalence check. If the root node of the two programs has merged into same E-classes, then good. Our process is done. It's finished. Otherwise, we will scan the current E-graph for the control flow candidate and inject the dynamic rules. This process will repeat it until we can confirm the equivalence for the input code, or no new dynamic rules can be generated, and the process will be converged. Now let's talk about the formal manner of the HEC. It is sound but not complete. It means HEC will never produce the false positive. If we declare the two programs is equivalent, then they truly are. Because our static rules is common proven static, the Boolean and the arithmetic identity, and the dynamic rules is proven using the SMT, these three SMT solver. However, HEC does have the possibility to provide the false negative. It means some of the equivalence may escape escape our rule set. If some of the equivalence, they have the semantic equivalence, however, our writing rules doesn't incorporate the corresponding writing rules, then it may produce the false negative. This is the result. We incorporate over 13 different benchmarks from the Zhan, the Lu, the Jiaqi, and our AI-based benchmarks, the CN forward. We will test for the control flow transformation like the loop unrolling, loop tiling, and the data path transformation. Finally, we will tell about the bugs we have generated in the PolyBench-C benchmark. This is the nested unrolling control flow transformation. For each of the x-axis, it means the unrolling factor for the nested unrolling. It means we will first unroll by factor k, and we will unroll the result again by the same factor k. The k is from 2 to 16. We can see both of the runtime and the E-classes count grow quadratically as the unrolling factor increases, because it shows the fact that the our code size is also quadratically increases. This is our data path transformation benchmark. We incorporated the benchmarks from 15,000 to 108,000 lines of the code. All of the benchmark can be completed within 14 minutes. And the static rewriting will dominate the end-to-end verification runtime. Finally, let's talk about the typical bugs we have identified in our MLIR code. In the left code, we will first read the data, and we will add the constant 1 to the element in the input array for each indices from 1 to 10. However, in the right code, we will fuse the code input, and however, the right code will crop the data dependence. We can see on the left code, the output, the correct output is all of the element is plus by 1 for the element except the index 0. However, for the right code, all of the element is incremental. So basically, the loop fusion in the MLIR compiler, it alters the execution order and brings incorrect semantic behavior. Such the read after write hazard can easily silently corrupt the result. Thank you very much. I'm glad to take any questions.